Very, very good. Okay, so good afternoon, everyone. My name is Prof Staunton. I'm from Warwick University in the UK. Just to say a little bit about myself, I carry out ab initio magnetic materials modelling, and I focus in particular on permanent magnets, so those materials containing rare earth and transition metals predominantly. I'm also interested in caloric effects, particularly in magnetic materials. For my sins, I'm also director of a doctoral training centre at Warwick that specialises in computational materials modelling. My brief is to discuss the coupling of magnetism with the lattice. So this is a very broad area. Clearly, magnetic exchange interactions are by how far apart the atoms are, or where they're located, etc. There's magnetophonon coupling, where the magnetic excitations affect and are affected by the lattice vibrations. What I shall do in this lecture, though, is to focus on one particular important, rather fundamental aspect of this physics, how the magnetism links to the lattice, and that's going to be primarily spin-orbit coupling. And what I'll do is to talk about it a little bit and then follow its ramifications for various effects. So I'll make just a few introductory remarks now, just to set the context a little bit. So, as you've heard already in the lectures so far, to understand magnetism in condensed matter, we have to consider the effects of the interactions of the electrons in the system and the consequences of their spins. So at a fundamental level, this means that the wave function that's describing these many electrons must be antisymmetric. So it's got to be consistent with the Pauli exclusion principle. This generates spontaneous magnetization in some materials, which can be expressed quite succinctly in terms of this sort of classic, well, not this famous Heisenberg-like Hamiltonian. It also leads to spin polarized electronic bands in metals. However, if you sort of stare at that for a little bit, you realize that there's nothing to link the electron spins or the spin moments to any spatial direction. So one has to think of what can generate this effect, because it's obviously a very important aspect of magnet, and it's spin-orbit coupling that is a prime factor in doing this. So this is where it's describing the interaction between the orbital moment and the spin moment. And I'll explain a little bit about what effects it can lead to. So it has the role in setting the magnetic easy axis and determining how magnetically hard a material is. So this is the case where if one was to pick up a perfect of, let's say, ferromagnetic iron, its magnetization would preferentially want to fall along a particular direction if it was a single domain particle, rather than being in any which direction. Spin-orbit coupling also sets the scale for the width between domains in a magnet. So you have a real magnet will be comprised of many domains, where the magnetization in one is pointing in a different direction from the magnetization in another domain. And then if one goes from one domain to the other, it's got to have some transition range, and that's the domain wall. And as I'll explain in a little bit, spin-orbit coupling is a prime factor in determining how thick the domain wall is. Following on, the spin-orbit coupling, so an electronic effect, and it has implications for spintronics. It's at the heart of the anomalous Hall effect, spin-orbit torque, etc. And I think later in this summer school, you'll hear some lectures about spintronics. The electronic structure itself is affected by topology, and once again, spin-orbit plays a big role. And moreover, the aspects it leads to can set the type of magnetic nanostructures that are formed in various systems these days. Okay, so let me just take a step back from the sort of sub-nanocell, which is the area I'm interested in when I'm looking at intrinsic properties, and focus on how one would describe a magnet on a sort of longer length scale. So if one writes down a free energy of a magnet in the expression at the top of this slide, so we've got magnetization profile in the system, So this could be capturing the domain structure and everything. And so one can characterize this, write down this free energy in a relatively straightforward form with some parameters. And the first term we have here with the A in front, this sets the scale for the energy cost when the magnetization deviates from being uniform. So A, from an intrinsic point of view, A is set by the exchange interactions. It's set by the transition temperature, the Curie temperature of the material. The second term, that's just the interaction between the magnetization and an applied field. The third term is a kind of effective demagnetizing field that's set up within the system because the system has a magnetic structure, which is the magnetostatic term. And then the last term, which I've put in red, is the piece that I'm going to spend most of the time on. So this is the anisotropy term. And so this is really, it's fundamentally coming from these spin-orbit coupling effects. So just as a recap, so it's a fundamental property, and it's linking the magnetization to structure via, as I said, spin-orbit coupling. If U is large, then this would be symptomatic of a material which is magnetically hard. So this is where the permanent magnets have large U. For small anisotropy, then these are the materials which have high permeability, very soft magnetically. If we're looking at stability of magnetic information, if we have smaller magnetic nanoparticles, then you want to preserve the information. So this would be the direction of the magnetization in the particle. Then you want that information, that direction, to be stable to stray fields and thermal fluctuations, etc. And you see, you talk about a blocking temperature. So this is the temperature above which that information can no longer persist. And so this is proportional to how anisotropic the system is, magnetically anisotropic the system is. This quantity is because it's dependent on spin orbiting, it's big for those materials with high atomic number. And as we'll see, it has strong temperature and compositional and structural dependence. Now, I thought I might just stop for a couple of minutes just to ask a question, if I may. Let me see if I can do that. So I want to stop sharing and I want to ask a question. Let's see if this works. First time I've tried it. So select poll. So I'm going to, what do I want to do? Just a yes, no question. So my question is then, in that free energy expression I showed, if that anisotropy energy was small, so if U is 0, is there any magnetic anisotropy still persisting? So if you'd like to just say yes or no. 1, brilliant. Okay, I think, no, we haven't quite finished. A few more time for people to think about it. Okay, I think we're about done. Okay, I'll give it 20 more seconds, I think. Okay, thanks very much. So let's end the poll. So now we go back to the application. Kill the browser. view again. Okay, so the majority had the right answer. Yes, the third term in this expression generates anisotropy, and this is dependent on the shape of the material. So its other name is just the shape anisotropy. Okay, so let me say a little bit more now about the anisotropy term that's coming from the spin-orbit coupling effect, this intrinsic effect, rather than a macroscopic effect. So typically, this energy can be captured in terms of a few coefficients. So these coefficients KL are then multiplied by some polynomials, and these polynomials are just really consistent with the crystal point group symmetry of the lattice. And what one finds as the temperature rises, that these coefficients decrease rapidly. And one can see this for yourself by looking at a model Hamiltonian for a magnet. So there it is in terms of a Heisenberg exchange term, and then a term that captures this anisotropy. So this is where there's an energy variation depending on whether the spins are parallel or perpendicular, for example, to some crystallographic direction n. So if one writes down that Hamiltonian and then you carry through some statistical mechanics for the model, so you can use a mean field treatment or whatever, then one can find out, you can characterize the magnetic anisotropy as a function of temperature and get a handle on these coefficients that you could then feed into your longer length scale magnetic modeling. And what one finds when you do this is that these coefficients decrease as a function of the extent of the magnetic order. So at low temperatures, if the anisotropy can be quite large, as the temperature increases and it's approaching towards Tc, then these anisotropy coefficients decrease quite significantly. And how they decrease depends on the structure of the material. So if the material has some sort of tetragonal symmetry, then this polynomial dependence you see at the bottom of the slide, this L, is 2. And so that means at low temperatures, these anisotropy coefficients will decay proportional to the cube of the magnetic order. And at higher temperatures, when you approach Tc, then the decrease is not so great. It decreases to the power 2. If one goes to materials with different sorts of symmetry, so cubic symmetry, this leading coefficient L would be 4. So here now the anisotropy coefficients decrease really sharply to the power 10, and 4 at higher temperatures, and so forth. So again, you can see how there's this spin-orbit coupling is really linking the anisotropy properties to the crystal lattice. Okay. So I come from doing ab initio modeling, so I just thought I'd show you a couple of results. So this was implementing this sort of approach in an ab initio setup, which I'll mention a little bit later. So what we did was try to calculate the transition temperature, the Curie temperature, for quite a strong permanent magnet. This is iron platinum, which is an ordered alloy of iron and platinum. It's known to have quite high anisotropy, and it's studied for magnetic storage and so forth. And what we found that you can consider magnetizing the system along a couple of different crystallographic directions. So you can magnetize it along the c-axis, so perpendicular to the layering, and see what the transition temperature would be. And we found that that was higher than if one looked for a solution where the magnetization was in the plane of the layers. So this is consistent then with the easy axis for this material being along the c-axis. And then again, applying basically sort of first principles picture of that statistical mechanical model that I just showed on the other slide, you could also show that the anisotropy coefficients decay for basically all temperatures to the power 2, to quadratic power with the magnetic order. So rather different from this sort of simple model of the anisotropy that we had earlier. And in fact, you see that that's symptomatic of some anisotropy appearing in the exchange interactions. And again, hopefully I'll have time to say a little bit more about that. So that's the next one. Okay, so that I've talked there about a fundamentally metal system. Of course, the most important permanent magnets in the world all contain rare earths, and that's because the rare earth materials can generate a very large anisotropy, and that's drawn from the distribution of their charge densities. So it's coming from their localized F electrons. And as I'm sure you're familiar, these configurations are determined by Hund's first and second rules. So, for example, for samarium, with its five 4f electrons, it has a total spin from these f electron configurations of 5 halves and a total angular momentum of 5. And so one has these f electron charge distributions set up in the material, and then spin-orbit coupling then causes this charge distribution to be essentially dragged around with spin as the magnetization direction is altered. And this generates an anisotropy. And so basically from the electrostatic energy cost from all the surrounding charges, namely the crystal field. Okay, I'll try maybe another little question. I think it's good to try this. So I'll generate this and stop sharing. Where do I stop sharing? Stop sharing. So another little poll just to, so this is multiple choice this time. So basically, I want to ask what's S and, oops, capital S, L for dysprosium. So dysprosium has got 9 4f electrons. So a couple of suggestions. Is it 2 and 6? Is it 3 halves 6? I won't add another one. Is it 5 halves 5? Okay, let's see what people come up with. So this is just from applying Hund's first and second rules, and then just thinking how the F electrons are distributed in the shells. Okay, so I think we've got a few more answers coming in. So I maybe just give 30 seconds more. Okay, I think we'll stop now. Oh yes, it's a good question. Yeah, I mean 3 plus. Should have said that. So go back to sharing the screen again. So yes, the answer was for 3 plus dysprosium ion is that spin is 5 halves and L is 5. So that's the third answer. The total J for this case is L plus S, whereas for samarium it's L minus S. Okay. Now I want to come on to showing really the implications of this spin orbit generated magnetocrystalline effect. So here's at the top of the slide is a very simple model of a block domain wall. So imagine we've got two regions, two domains, and have an interface between them, which is the domain wall. So on the left, the magnetization in the domain is pointing upwards along, let's say, some z-axis, and to the right, it's along the it's anti-parallel to that, it's pointing downwards. And then the intervening space, the magnetization direction is changing continuously. Someone can model this with that free energy expression as showed earlier. So in this case, the magnetization is specified or just proportional to this vector involving 0 and sine theta cos theta. So the x direction. And so I should say here that this magnetic profile is established because we're not treating the shape anisotropy in this case. We're assuming that it's determined the domain structure already. So it's said that that there's two domains and the magnetization is pointing up in one domain and down in the other. So with that limitation, with those boundary conditions applied, we can now look at the free energy and try to minimize it to find the magnetic profile. And so now the free energy simplifies into the term shown on the slide here. So you've got the term coming from the exchange, the energy cost for how the magnetization varies throughout the system, and then this piece coming from the anisotropy. So it's some coefficient capturing this effect, and the direction, the cosine squared of the direction of the magnetization with some crystallographic direction. In this case, it's just the z direction. So you write down that free energy, and subject to these boundary conditions, that the angle is up in one direction, down in the other, you minimize the free energy. And out comes a nice differential equation that will, the solutions of which will give you the magnetic profile. So it's quite a famous equation. So it's close or very similar to the nonlinear sine-Gordon equation, and its solutions have the form shown on the bottom of the slide here, which I can just plot out. And so on the y-axis, I've got the angle in units of pi, and then we've got the along the x direction. So -1 is where in one domain, and x equals +1 is in the other domain. And you can see now that this angle is varying over some region, and one can work out from this equation what is the width of the wall, and it's the square root of the exchange coefficient to this anisotropy coefficient. So one can learn from that relatively simplified model that spin orbit coupling generated anisotropy is determining how thick or thin a domain wall is. So the stronger the anisotropy, the more narrow the domain walls are.
So originally there was a point in the chat translated to, shall you consider free energy or energy? Does that matter?
In principle, I'm thinking of a free energy of a material, so I'm thinking of as a longer length scale description of the material. But I suppose one in principle could carry out this also at 0 temperature and would have the energy of the system. hope that answers things.
And then there was another question. You write that the width of the wall is square root of a over k.
Yeah.
Sometimes it is written pi square root of a over k. Does that matter? Which one is better?
Good question. I'll try and wriggle out of that by saying I haven't got any an equal sign here. I've got a tilde.
Okay, I would push that to the questions then.
Yeah, sure. Yeah, so the piece I wanted to bring out, that's good. Yeah, the units are right. Is to point out that the walls get narrower the bigger the anisotropy. Okay. Now, I mentioned the blocking temperature, so the stability of magnetic information. So this is whether some area in a material has its magnetization pointing along one direction, so it's like capturing one bit of information, and somewhere else it's pointing down. So you've got the expression for bits and so on. And here's some experimental and theory comparison. So on the right is some measurements of the blocking temperature. So this is the temperature above which this magnetic information is no longer stable. So stray fields, etc., will kill it. And there's I think really beautiful experiments. So what they did was to take a platinum substrate, and they placed little nano discs of cobalt on the surface. And those cobalt discs at low temperatures had a preferential direction out of the plane. And then they plotted this, how stable that direction was as a function of how big the disk was. And as one might expect, the bigger the disk, the higher the blocking temperature. It retains its information to higher temperatures. And then what they did after that was they started decorating these discs. So they started putting sort of a monolayer of iron around these discs, and then compared it with what happened if they just put a monolayer, deposited some platinum atoms around the disc. And they found that the blocking temperatures were quite significantly different. In fact, by embroidering the discs with iron, made this blocking temperature go up quite nicely, so it would retain its information to higher temperatures. So that was the blocking temperature. And then, so what these calculations did was then to make a calculation of the anisotropy coefficient under these circumstances, modeling these systems. And again, they found that these trends were captured pretty nicely. So it's showing how this stability of magnetic information is really connected to the magnetic anisotropy. Okay, so as I keep going about ab initio modelling, I'll just say a few words about that. What I would just like to do is just to see people's familiarity with this. So this will be a very, very quick poll. So let me just stop sharing. So a very quick poll. Multiple choice yes, no's answer. So I just want to know how many people are familiar with electronic density functional theory. So we'll just characterize how. Okay, quite a mixture. Okay. Okay, so I think that gives me the information I want. So I'll go back to sharing the screen. Cool. Okay, so thanks for that information. So as I said, I do want to say a little bit about this density functional theory, which some people are familiar with, but I think the majority are not. So this is a method that's used in a very widespread way these days in modelling materials sub-nanoscale. If, as ever, the materials modelling has to describe, in principle, should describe all the many interacting electrons in the material. And what this theory does is to actually make this problem tractable. So there was a Nobel Prize awarded some 20 years ago to one of the inventors of this method. What it really does is it focuses on the energy of a material, even the ground state energy of a material, in terms that in principle have some horrendous dependence on some many electron wave function with Pauli exclusion principle incorporated, etc. And what it then does is to say that actually this energy can be written down in terms of the electronic charge density and the magnetization density. So they say it has this functional dependence on the distribution of charge, the charge profile, and the magnetization profile in the material. So this is, we're thinking about a perfect single crystal at the moment, but it can be generated to any material. Then the theorems that lie at the heart of the framework say that the actual charge density and magnetization density that you have in this energy are found by minimizing this energy with respect to these profiles. And then the beauty of the method is that this minimization process can be then just recast in a form where what you have to do, instead of solving for many electrons, what you do is to solve a Schrödinger equation for a single electron, moving in effective fields that are set up by all the other electrons. So now one can throw computational power to solve something where there's a lot of expertise around. And these, if people know about density functional theory, these are the Cohn-Sham equations. So it has a long history. So it has the same flavour as a Hartree-Fock description of treating description of electrons in the material. So these effective fields have all the subtle exchange and other many electron effects embedded in them. And these are particularly profound or particularly subtle for materials that contain nearly bound DNF electrons, as we have in many magnetic materials. And so these days it's possible to also incorporate the effects of spin-orbit coupling, use the computer power to solve these equations, and then output things like the magnetization of the material. One can then incorporate finite temperature effects and understand how the properties vary with the function of temperature, etc. In particular, one can evaluate the difference between this energy if it's magnetized along one crystallographic direction, and see how it's different from if it's magnetized along another. And then from that, one can generate the magnetic anisotropy, which then you could feed into generating some magnetic crystalline anisotropy coefficient for these longer length scale models of magnetic materials. So that's in a nutshell what lies at the heart of this modelling. Are there any questions about that? I appreciate this. Maybe I will come to that perhaps towards the end. I wonder, should we, is it time for a break yet, or in about 10 minutes?
You still have 10 minutes, but I have a question from Maxime, actually, which is, can you remind us why we have to focus on the free energy?
Free energy, just keeping that, so we're looking at finite temperature, the material at finite temperature. So maybe it's just a semantic choice.
Okay, is there any more question at that point? Or shall we continue? 5 seconds. If not, then yes, 10 minutes before the break.
Okay, all right, thank you. Yeah. Okay, so I don't want to throw. I've got this one slide just to give the background to density functional theory for those that are interested. So it's coming from sort of first principles. So one really goes towards the level of looking at the quantum electrodynamics of the many electrons. And so from that, the theory can be generated such that from that basis, so really understanding the many electron effects, you then can write down this energy in terms of 3 pieces. So this is at zero temperature. So it's the piece that's connected to the kinetic energy of the electrons. It's the Hartree energy, and there's the exchange correlation energy, and then the interaction of the charge and magnetization densities with the applied any external field. And then the story behind DFT goes that this is minimized and will give the appropriate ground state charge and magnetization densities by solving these one electron cone-sham equations. And in this case, where we're really putting in all the spin orbit coupling effects and so forth, so we're having to allow for relativistic effects. If one's a purist, then what you're doing is then solving these cone-sham Dirac equations. And so I've just got them there so you can look at them later if you're interested in. So in principle, we've got one electron, effective electron, and it's moving through these effective fields that are set up by all the other electrons. And then what one does, you solve this Dirac equation, or if you're looking at the non-relativistic counterpart, that's Schrodinger equation. You make a guess for what this charge density and magnetization density is. Then one generates these effective fields and effective magnetic fields. And one puts them into the Schrodinger or the Dirac equation, solves these for the wave functions, and then calculates the charge densities from those one electron wave functions. So it's just summing up, taking account of all the electrons you have in the system to obtain the charge and magnetization densities. And then one keeps doing that until you have a so-called self-consistent solution. So this is again a reason why you need fairly big computers to carry out this this procedure. So that, again, that's just adds a little bit more to this story. Okay, so let me just lead to something probably looks a bit more intuitively reasonable. Now, if we sort of distill out the leading relativistic effects from this, so if we want to look at the leading corrections, so with 1 on the velocity of light squared leading terms, and then from this one finds that you get a Schrodinger equation or Pauli-Schrodinger equation to emerge, where you've got the familiar terms that you have in the Schrodinger equation, plus some corrections from the relativistic effects. And of course, the one I've been talking about is spin orbit coupling, but there are 2 others. There's the mass velocity correction, which is basically the corrections to the kinetic energy, and this Darwin term, which is consequences of fluctuations of the involving the fluctuations of the electronic movement with some of the potential of the system. But it's the spin orbit coupling that I'm going to focus on here. So, and this is the form it has. So it's some electric field cross product with the momentum, dot product with the spin. And if from quantum mechanics courses, if you were to put a spherically symmetric potential in there, you would get the you would see how to get the L dot S term coming out. And so here's these calculations have been around for some time, so I show some old plots of what it does to the band structure of a material which has a large Z, platinum, Z of 78, if I remember correctly. So these are the bands along the gamma X direction. Platinum has a face-centered cubic structure. And so one can see here, you've got basically like a free electron-like band cutting across some more narrow D bands. And there's hybridization showing the actual distribution of the bands. The dotted lines are just showing, indicate what would happen without the hybridization. Now, if you turn on these relativistic effects, there's some shifts to the bands coming from these mass velocity and Darwin terms, but there's also some breaking of the degeneracy, which is coming from the spin-orbit coupling. And it's, again, the heart of all these effects as I've been mentioning. So you see at the gamma point, the Brillouin zone center, some degeneracy is broken here. You've now got three bands. Similarly, at the X point, we've also got some breaking of the degeneracy. So that's kind of the takeaway message on that aspect. And these days, these effects are attracting a lot of interest in the world of looking at topological insulators, where you have some fortuitous degeneracy, and then spin-orbit coupling comes along and breaks that degeneracy and opens up a gap. So that's one key feature. So again, let me just, yes, this is a good point to my last poll then for this piece. So if we're going to break, so I just stop sharing screen. So my poll, okay, multiple choice. It's kind of one of these quite interesting facts, I think. So let's just see. So what color is gold if you ignored relativistic effects? So let's go through the answers. Red, yellow, blue, and what was the last one? Oh, let's keep it boring. Okay, so let's start. So if we neglected gold, I wonder if anybody knows this. Interesting. Okay. So, okay, end of the poll. Okay, so the there's still a few more answers. Okay, since it's the break, I'll stop the poll now. The answer actually is without relativistic effects, gold would appear shiny like silver, so it would be white. So what happens is that gold absorbs blue light more than the other visible wavelengths, so therefore it appears yellow. And this is down to the 5D 6S transition being affected by these relativistic effects, sort of to narrow that energy difference. Whereas in silver, you've got the analogous 4D to 5S distance. It has a smaller Z, so the spin-orbit coupling is less. The distance is much greater and essentially therefore appears shiny white. Okay, so that brings me back to half one, so I think I'm done for a bit.
Very much. So I have several questions from the audience. Have questions.
Okay.
So the first question is, are there also other effects that can lead to magnetic anisotropy in spite of spin-orbit coupling?
I don't think so. I think I think it's spin-width at an intrinsic level. It's spin-width coupling, and the effective magnetic field that's set up by the magnetic distribution in the material. So this is the shape anisotropy. So I don't think I know of any other effect that would lead to an anisotropy. Yeah. And so there's the two key aspects that appear in the modeling of the material.
Okay, thank you. Then I have a question about Taro Komori regarding page 9. I think it's slide 9. I think what he meant. How is the torque, the partial derivation of the energy with respect to n, related to magnetic anisotropy? Or can we consider that the torque is exerted onto the magnetization?
Okay, that's a good question. I wonder if I should just show. Maybe I don't need to show. So it's equivalent. So what one does is to write down the expression for the energy given that the system is magnetized along a particular direction, n. And now one just looks at variations of that energy when you change that direction very slightly. So you get this essentially this derivative. Now, if one knows that the form of the anisotropy is in terms of these coefficients and some simple polynomial, one then can differentiate that and then link this torque to those anisotropy coefficients. So it's just a numerically more robust way of getting at these anisotropy energies. I hope it's quite a long answer, but I hope that answers the point.
I guess he can tell us in the chat.
The end of the question is also, can we consider that the torque is exerted onto the magnetization?
Yes, that's right. Yeah. And
I think Oksana will come back to that in detail during her lecture, especially on micromagnetism.
Exactly. Yes.
And the last question is about these colors. The last poll, which was really interesting. So, why is copper being 3D goldish in color?
That's a good
explanation. That's the.
I don't know. Good question. Yeah, we should find out. I presume there's some other transitions involved, but that's very good. Good point.